Okay, we are going to study for the ham general exam. So this is not the technician class. I'm already a technician. We're moving up to general. And um, I've gone through sub-element 1, 2, and 3. I went through 1 and 2 by watching YouTube videos. I went through those because I can't really learn very well just by reading it. I have to interact with it in some way, have somebody explain it or something, or it doesn't stick. I went through sub-element 3 and I played around a little bit in here with ChatGPT 5, ChatGPT 5, and it was kind of useful. I only did a couple questions, had ChatGPT help me. So we're going to go into 4 and sub-element 4, and we're going to just see how this goes using ChatGPT to help us learn. And I've never read any of these questions in 4. This is literally the first time I've opened it, and we're just going to go. So let me open up ChatGPT on my phone. And we'll see how useful, if at all, this is. Okay, we're going to move on to sub-element 4. Are you ready?
Absolutely. I'm ready to go. Let's dive into sub-element 4 whenever you are.
All right, sub-element 4. First question. What is the purpose of the notch filter found on many HF transceivers? It says the answer is to reduce interference from carriers in the receiver passband. Can you explain that a bit?
Absolutely. So the notch filter on an HF transceiver is basically a tool to help you deal with annoying interference. Imagine you're listening to a signal and there's this steady tone or carrier right in the middle of the frequency you're trying to hear. It can be super frustrating because it just sits there and makes it hard to hear what you actually want to listen to. What the notch filter does is it lets you notch out or remove that interfering tone. It's like telling your radio to ignore a very narrow slice of the frequency spectrum where that interference is sitting. By doing that, you can hear the signal you actually care about much more clearly. So in short, the notch filter is all about reducing interference from unwanted carriers so you can focus on the signal you actually want to hear.
Thank you. Let's move on to the next one here. What is the benefit of using the opposite or reverse sideband when receiving CW? The answer is it may be possible to reduce or eliminate interference from other signals. Can you talk about that one?
Absolutely. So when you're listening to CW, which is Morse code, on a sideband receiver, you usually have the option to switch between upper sideband and lower sideband. And using the opposite or reverse sideband can sometimes help you dodge interference. Here's how that works. If there's a signal or some kind of noise sitting on one sideband, switching to the opposite sideband can sometimes move that interference out of your passband, or at least reduce it so it's not as loud. It's kind of like changing the angle of your filter to find a quieter spot to listen to that Morse code signal. So the benefit is that by flipping to the other sideband, you might be able to either reduce or completely get rid of interference that was bugging you on the original sideband. It's a neat little trick to get a clearer signal.
Thanks.
You're very welcome. Anytime you need more explanations or want to dive into the next question, just let me know.
Yeah, let's go to the next one. It says, how does a noise blanker work? And the answer is by reducing receiver gain during a noise pulse. What the heck is a noise blanker?
Absolutely. Let's break it down. So a noise blanker is a pretty handy feature on a receiver that helps deal with pulse type noise. This kind of noise could be things like ignition noise from a car engine, lightning crashes, or other short bursts of interference. What the noise blanker does is it detects those quick noise pulses and momentarily reduces the receiver's gain just during that noise pulse. Basically, it turns down the volume on the noise for a split second, so you don't hear that burst nearly as loudly. In other words, it's like a little automatic mute button that kicks in just for those noise spikes. And this helps you hear the actual signals you want to listen to without being blasted by those brief but annoying noises. So that's the magic of a noise blanker.
Do most radios have those, or is that like a feature on high end ones?
Yeah, good question. So, actually, a lot of HF transceivers, even quite a few mid range ones, do come with a noise blanker feature built in. It's not usually something that's only found on the really high end radios. Even Benny's more affordable or mid tier hit radios have some kind of noise blanker because it's such a useful feature for dealing with those common types of interference. So, chances are, if you have an HF rig, there's a pretty good likelihood it has a noise blanker in there somewhere. It's definitely a common and handy tool to have.
All right, moving to the next one. What is the effect on plate current of the correct setting of a vacuum tube RF power amplifier's tune control? And the answer is a pronounced dip. I don't have any clue what that means.
Yeah, no worries. Oh, this one's a little more on the technical side. So let's break it down. When you're tuning a vacuum tube RF power amplifier, you're basically adjusting the tune control to get the amplifier to operate at its most efficient point. Now, one of the ways you can tell you've hit that sweet spot is by watching the plate current, which is basically the current flowing through the tube. When you adjust that tune control correctly, you'll see a noticeable dip or a drop in the plate current reading on the meter. And that pronounced dip is a sign that you've tuned the amplifier to its optimal point for that frequency. So, in other words, you're looking for that little drop in plate current as a visual cue that you've got everything tuned up just right. Once you see that dip, you know the amplifier is working efficiently and you're good to go.
So the pronounced dip is what you're looking for?
Exactly. You got it. That pronounced dip in the play current is basically your little sign that you've tuned everything correctly. It's what you're aiming for to know that your amplifier is running efficiently. So once you see that dip, you're good to go and everything's tuned up just right.
Thanks. Let's see the next one. What is automatic level control (ALC) used with an RF power amplifier? Or sorry, why is not what? Why is automatic level control used with an RF power amplifier? And the answer is to prevent excessive drive. Any input on that one?
Absolutely. I can definitely shed some light on that. So, automatic level control, or ALC, is basically like a safety mechanism for your RF power amplifier. Its job is to make sure that the signal driving the amplifier doesn't get too strong. If you send too much drive or too strong of an input signal into the amplifier, it can start to distort or even damage the equipment. So the ALC steps in and automatically adjusts or limits that input level to keep everything within a safe range. In other words, it's used to prevent excessive drive so the amplifier doesn't get overdriven and you get a clean, distortion free output.
Pretty straightforward. Let's move to the next one. What is the purpose of an antenna tuner? The answer is to increase power transfer from the transmitter to the feed line. I think I'm okay on this one, but go ahead and talk about it if you would.
Sure thing. So, an antenna tuner is basically a device that helps match the impedance of your transmitter to the impedance of your antenna system and feed line. When everything is matched up properly, you get maximum power transfer from the transmitter into the antenna, which means your signal can get out more efficiently. In other words, if there's a mismatch, like if your antenna isn't quite the right length or your feed line has a different impedance, the antenna tuner steps in and acts as a sort of middleman to make everything look like a perfect match to the transmitter. This helps ensure you're not losing power and that your signal gets out as strong as possible. So yeah, in a nutshell, the antenna tuner is all about making sure you get the best power transfer from your transmitter to your antenna system, and that just helps your overall efficiency.
Yeah, I think this was a similar question on the technician exam, but the answer was to basically match your impedance. So that's the way I think about it, but they have a different answer here, but it's kind of the same thing.
Yeah, you're absolutely right. It's basically the same concept, just described in a slightly different way. On the technician exam, they often say the antenna tuner is there to match impedance, which is exactly what it's doing. And that impedance match is what ensures maximum power transfer. So it's really just two ways of talking about the same idea. Right? As long as you think of it as the tuner making everything match up, so your signal gets out efficiently, you're spot on.
All right, question 7 in subelement 4. This is what happens as a receiver's noise reduction control level is increased? And the answer is received signal may become distorted. I think I got that one okay, but let's hear what you have to say.
got the gist of it. So the noise reduction control on a receiver is really helpful for cutting down background noise and making weak signals easier to hear. But as you turn that noise reduction up higher and higher, the receiver has to do more processing on the audio, and that extra processing can sometimes cause the signal to sound a bit distorted or unnatural. So it's really a trade-off. You're reducing the noise, but if you push the control too far, the audio quality might suffer a bit, and the signal can get a little distorted. It's all about finding the right balance so you get clearer audio without losing too much quality.
Great. All right. Question 8. What is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? The answer: desired power output without exceeding maximum allowable plate current. Can you elaborate?
Absolutely. So when you're adjusting the load or coupling control on a vacuum tube RF power amplifier, what you're doing is kind of fine-tuning how much power is being transferred from the amplifier to your antenna system. You want to get the power output to the level you want, but you also have to be careful not to let the plate current go beyond the safe limit for the tube. So the correct adjustment is really about finding that sweet spot. You adjust the load or coupling control so that you're getting the desired amount of RF output power, but you're not pushing the plate current above its maximum allowable rating. That way you're operating the amplifier safely and efficiently without risking damage to the tube. So it's all about balancing that power output and keeping the plate current in an safe range.
Can you talk a little bit more about what plate current is?
Absolutely. So plate current is basically the electric current that flows through the plate or anode of a vacuum tube in an amplifier. In a vacuum tube RF amplifier, the plate is one of the main elements inside the tube that helps amplify the signal. When you apply a voltage to the tube and you have a signal going through it, the plate current is the measure of how much current is flowing through that plate. It's an important parameter because it gives you an idea of how much power the tube is handling and whether you're operating it within safe limits. If the plate current gets too high, it can mean you're driving the amplifier too hard, which can cause distortion or even damage the tube. So when you're adjusting things like the load or the coupling, you're keeping an eye on that plate current to make sure it stays in a safe range. And that's really all it is, just a measure of the current through the tube that helps you keep everything running smoothly.
Great. Okay, question 9. What is the purpose of delaying RF output after activating a transmitter's keying line to an external amplifier? Says the answer is to allow time for the amplifier to switch the antenna between the transceiver and the amplifier output. Can you describe this one?
Absolutely. So this is all about timing and making sure everything switches over smoothly when you key up your transmitter. When you're using an external amplifier, that amplifier needs a moment to switch the antenna connection from just the transceiver over to the amplifier and then out to the antenna. If you didn't have that brief delay, you might end up transmitting before the amplifier and antenna are fully ready. That could cause a little bit of signal loss or maybe even a click or pop in the transmission. By adding a short delay, you're giving the amplifier that little bit of time it needs to switch everything over so that when you do transmit, everything is lined up perfectly. In short, it's just a little timing buffer to make sure the amplifier and antenna are all set before you start transmitting.
How does that work? What exactly are you doing to delay the RF output?
Yeah, definitely. So what's happening behind the scenes is usually just a small built-in timing delay. Many modern transceivers or amplifiers have a feature that introduces a brief pause, maybe just a few milliseconds, between when you hit the key or push to talk and when the RF output actually starts being transmitted. This delay is usually controlled automatically by the radio or amplifier itself. It's just a tiny built-in delay circuit that makes sure everything's in place. So you don't have to manually do anything. The equipment just pauses for a fraction of a second to let the amplifier's relays or switches move the antenna connection over. And then, once everything's ready, it lets the RF go out. So it's just a little automated timing trick to make sure things are lined up and ready to go before you start transmitting.
Okay, that makes way more sense. Thanks.
You're very welcome. I'm glad that helped clear things up. Feel free to keep the questions coming. I'm here whenever you need me.
Yeah, let's move to question 10. What is the function of an electronic keyer? And the answer is Automatic generation of dots and dashes for CW operations. So I don't think I need you to explain this one. I think I'm good. Are you okay if we just move to question 11?
Absolutely. If you're feeling good about that one, we can definitely move right along to question 11. Just let's dive in whenever you're ready.
All right, question 11. Why should the ALC system be inactive when transmitting AFSK data signals? The answer, the ALC action distorts the signal. Can you talk about that one?
Absolutely. So this is a good one to dive into. When you're transmitting AFSK data signals, basically audio frequency shift keying, which is often used for digital modes, the idea is to keep the signal as clean and consistent as possible. The ALC, or automatic level control, is usually there to prevent overdriving the amplifier, but when it kicks in, it can actually change the audio levels dynamically. And for a data signal, that can cause distortion. In other words, you want your AFSK tones to stay at a steady level so that the receiving station can decode them accurately. If the ALC is active, it might start adjusting the levels, and that can distort the data tones, making them harder to decode on the other end. So the idea is to turn off or minimize the ALC when you're sending AFSK data so that your signal stays clean and you get a nice undistorted transmission. So that's the reasoning behind it.
So essentially, if you use an AFSK, make sure your ALC is turned off, and that's just to avoid distortion.
Exactly. You got it spot on. It's really just about keeping that ALC out of the picture so your AFSK signal stays nice and clean. That way you avoid any distortion and the receiving station gets a nice clear data signal. So that's the key idea.
What is AFSK?
Sure. So AFSK stands for Audio Frequency Shift Keying. It's basically a way of sending digital data over the radio by using different audio tones. So instead of directly shifting the radio frequency itself, your radio stays on a single frequency and the data is turned into audio tones that represent the ones and zeros of digital information. Those audio tones are then fed into the radio's microphone input or another audio input, and the radio transmits those tones. On the receiving end, those tones are decoded back into digital data. So it's a pretty common way to do things like RTTY, PSK31, and other digital modes. It's all about using audio tones to carry your digital information over the air.
Excellent, thank you. Question 12. Which of the following is a common use of the dual VFO feature on a transceiver? The answer is to transmit on one frequency and listen on another. Can you go into that one?
Yeah, absolutely. So the dual VFO feature on a transceiver is really handy, especially if you're doing something like working a split frequency operation. Essentially, having two VFOs, or variable frequency oscillators, lets you set one frequency for transmitting and a different frequency for receiving. This is super useful in scenarios like DXing, where the station you're trying to contact might be listening on one frequency, but transmitting back on another. By using the dual VFOs, you can easily keep track of both frequencies and switch between them without having to manually retune each time. So it's a really convenient feature that gives you a lot of flexibility in how you operate.
Great, thank you. Question 13. This is the last one in this sub element. What is the purpose of using a receive attenuator? And the answer is to prevent receiver overload from strong incoming signals. I think that's pretty straightforward, but how about you go into it a little bit?
Absolutely. Happy to explain that one. So, a receive attenuator is basically a tool that helps you deal with signals that are just too strong. If you've got a very strong signal coming in, it can overload your receiver, and that can cause distortion or make it hard to pick out weaker signals. What the attenuator does is it reduces the strength of those incoming signals before they reach the receiver's sensitive parts. By knocking down the signal level a bit, you prevent the receiver from getting overwhelmed, and that makes it easier to hear everything more clearly. So in short, it's a way to protect your receiver from really strong signals and keep everything operating smoothly, especially in situations where you have a lot of powerful stations nearby.
Thank you. So we did 13 questions. We went through sub element 4, G4A. There's also G4B, G4C, G4D, and G4E just in sub element 4. It took us about 20 minutes to go through 13 questions. I think there's about 400 plus questions on the whole exam. So if we continue at this speed, how long will it take us to go through all 400 questions?
Yeah, absolutely. Let's do a little bit of quick math. So, if it took about 20 minutes to go through 13 questions, and there are roughly 400 questions total, we can just figure out how many sets of 13 are in 400 and then multiply that out. So, 400 questions divided by 13 questions per 20 minutes is about 30.8 sets of 13 questions. If each set takes 20 minutes, then 30.8 sets times 20 minutes per set is about 616 minutes total. And if we convert that into hours, that's about 10.3 hours or so. So roughly, if we kept the same pace, it would take around 10 hours total to go through all 400 questions. So just a little over a full day of really focused study time.
Perfect. That's very useful. Well, I'm going to end it for tonight, and I appreciate it. Thanks.
You're very welcome. I'm glad it was helpful, and it was fun going through those questions with you. Whenever you want to pick it up again, just let me know. Have a great night.
All right, I killed ChatGPT. So, yeah, I mean, super, super awesome. A great way to learn, in my opinion. So, like I said, when I did the technician exam, I found some videos of somebody just going through the questions, and then I just started taking a bunch of tests. And I'd watch the video once and I'd pause it. Pretty much every question I'd pause it and just kind of read it myself. And then I'd listen to what the guy had to say on YouTube. And then I'd read it again. But you couldn't ask any questions. If he just went through something quickly that didn't make sense, there's nothing you could do. So it's been very helpful. You got to be careful with ChatGPT. You don't know if all the information it's telling you is absolutely correct. But I think for the most part, it wasn't incorrect, and so I think this might be a pretty helpful way to study. Sounds like it'd take probably, let's say you put an hour into it every night, it'd probably take about 2 weeks to get through it all. And then if you maybe went through like 30 questions a night and then did a practice test once or twice, so you do like an hour. Yeah, it seems like in a couple weeks we could probably be ready for our general. So anyway, interesting stuff. I'm wondering if I keep doing videos or if I just do it on my own without the videos. But I think that was a pretty helpful way to learn. I'm ending it here.